So this talk is called Dream the Stream, High Velocity Event Processing with the Converged Database. It's a talk that's a mix of some high-level concepts and a little bit of marketing slides and some tech mixed in. I'm happy to talk with anybody after this call or even during about deeper under the hood kind of technology advancements in this space. Okay, let me go forward. Okay, so here's the agenda. I want to just give an overview of what is event stream processing. And then I kind of shift a little bit in terms of converged databases versus specialized databases. And we'll talk more about this, but this is the idea of having a specialized database just for event stream processing or any other type of workload, graph, spatial. There's lots of specialized databases versus what we call a converged database, which is a database that handles all different types of workloads. So we'll talk about that very quickly. And then I'm going to talk about in more detail what an event stream processing database needs and all the requirements and how, in this case, Oracle meets them with its technologies. And we'll go into that. Then, time permitting, I have some demo slides that go through an example of how we use the database for an event stream processing solution. Okay, feel free to interrupt me anytime you have a question, by the way. Okay, so what is event stream processing? So event stream processing really has three components. One is continuous ingestion. We're going to be ingesting high frequency event data, right? Rapidly bringing it into your system. The second thing is real-time analytics. So what do you do with that data? So you want to be able to process that data in real time. If this data is coming from a fleet of servers that's indicating the temperature, you need to know right away if any of those servers exceeds some temperature threshold, because you want to be able to resolve that so any customers running their applications on that server aren't impacted. And then the last part is data reorganization. And here the idea is, because you've ingested so much data that over time, you're not going to be able to keep that data either in memory or flash or whatever. You want to be able to move it off to colder storage. And you want to be able to compress it or summarize it so that when the data is at rest, you can still be able to store as much data as possible. Okay, so that's kind of the high level. What is event stream processing? Now, what about the data itself? What kind of data do we receive? So normally each event is like a discrete data record, and it comes from like a large farm of data sources. And those sources could be a variety of different things, right? It could be like just devices, sensors, meters, like your electric meter or gas meter, servers, if it's a DevOps monitoring scenario, desktops, or smartphones for that matter, right? So a variety of different devices. Think of the Internet of Things kind of scenario. And it typically consists of the following information. So if you look at these three different examples, on the left side, you got a meter reading, and there's always going to be a timestamp. There's an ID associated with the device where it came from. And then there's a reading. And the reading itself is, the value associated with that metric, as well as some attributes. So in this case, the reading just shows all of the values, like electricity used was 0.4 kilowatts per hour, 5 gallons were used, 2 gas therms were used. So this is an example of a meter. In the middle, you have a phone, again, timestamp and an ID. And similarly, the times of attributes are like the GPS location of it, the battery level, right? And the same thing on the right-hand side with cars. You got, GPS location, how fast was it going at this time? What direction was it going, and so on. Okay, so that's like event data. Now, the properties of event data are, as I mentioned, a very high arrival rate. Okay, we're receiving tons of data coming from different sources. And one example is like a billing system that's receiving millions of smart meter readings every few minutes. The second thing is this high obsolescence rate. So what that means is when the events come in, they're hot and they're the most recent data, and you want to do reports directly on it. And now the older events are going to be used more for like historical reporting that says something like, hey, in the last quarter, what was my average temperature reading, for example? Okay. And then, as I mentioned, these events then do get compressed and summarized as the data gets older and older and older. So if you look at the picture on the right, you see recent events going down to older events, and eventually they get archived. Okay. Okay, so now what are the requirements of an event stream processing system? So number one is, in our view, you want a flexible data model. And the reason here is that you are going to receive events from a variety of different data sources, and those events could have a different representation, may have a lot more attributes than other events. And you're building a data store engine for this. You don't want to have to keep changing your schema to accommodate for new attributes. And so, as we'll discuss, for a flexible data model, we like to use JSON. And JSON is schema-less. It allows me to change things on the fly as needed. The next thing, as I mentioned, is high-speed ingestion. That's a requirement. You're going to have to be able to sustain billions of events per day. So whatever system you build needs to be able to scale out and parallelize and be able to ingest rapidly. The third thing is, whatever system you build has to have a rich analytic query capability. As I mentioned, you're doing real-time analytics on this, but what kind of analytics are you doing? It's not just simple aggregation and counts and predicate evaluation. You want to do prediction, and you want to run ML against it. You want to be able to do things that are more complicated as you're streaming this data in. The fourth thing here is this real-time analytics capability. I want to be able to respond immediately and be data-driven. And so that generally requires me to run at in-memory processing speeds, right? I don't want to be bounded by I/O. I want to be bounded by CPU and potentially bounded by memory as well. And the last thing is, you need to have some kind of lifecycle management built into your system. You want to be able to do automatic data compression, automatic summarization of your data, automatic archiving after some period of time of unbounded growth. Okay, any questions so far on this? Okay, so now let's look at this converged versus specialized database story. So there's an increasing complexity due to modern apps. Modern apps basically use a variety of different data technologies. We have lots of new data types, text and graph and spatial documents, a lot of new types of analytics that are happening, machine learning, social graph, networks, and then different workload types, right? So because of these different technologies, it's making building systems more complicated. And that complexity then introduces more problems, like more bugs, have to deal with security concerns. How do you deal with upgrades? If one system needs to be upgraded, how do you deal with interfacing with another system? So it brings more complexity to the systems that we're building. So now, one approach is to build a specialized database for each application. And each specialized database can excel at that app's requirements, but they don't, it's like a one-trick pony, as they say. It's only good at one thing. So you see all of these different specialized databases that are built for these different types of data analytics and workload types. And we believe that the specialized database has a lot of problems associated with it. So number one, it requires that the application architecture that you're building is heterogeneous and distributed. You're working with a variety of different systems built by different people, that some of it might be open source, some of it may have some support associated with it. And if a problem goes wrong, right, it's like it brings unnecessary complexity to the entire system. So a lot of moving parts there, and your data becomes fragmented because some of it might live on one system, then it has to be transferred over to another system. And there's another big problem, is that these different specialized databases have limited asset consistency, right? You might have a very different asset model on one system versus the other. And so this is why we feel like the right approach is a converged database. So I'll talk about that in just one second. If you look at these different event stream processing solutions, this is just for event stream processing. You have your InfluxDB and your Prometheus and Timescale and so on. So lots of different systems built for one particular workload. Okay, so what we have and what we believe in is a converged database. Oracle is a converged database in that it supports all the modern data types and your workloads in one product. It just allows you to have different workload types and different data types, but all fit along the same components. So if you look on the picture on the left, JSON and graph and text, all of that is supported under one converged database. And it's got a lot of benefits, right? You don't have to worry about a unified security across all of these systems. You don't have to worry about data transfer from one system to another, and so on. And a good analogy is like a smartphone, okay? In the past, you had a separate phone, you had a separate camera, a separate video recorder, separate GPS, separate music device. Most of you guys have probably only known about smartphones, but before smartphones, you had all of these other different devices, and now everything is fit in a smartphone. And so that's kind of a great analogy. It all works on just that phone. You don't need to have all these other separate devices. Okay, so that's our model. We believe in this converged database to be able to handle all these workloads. So now going back to an event stream processing database and what does it need? So let's go to each one of those. So flexible data model. So we start off with JSON. Okay, and why do we think that JSON is necessary? So if you look at this, event stream data, again, is highly dynamic. As I mentioned, the formats can change. Instead of your reading values can change over time, the attributes associated can change over time. So we like to have a single schema, like the one on the bottom left, where you have essentially a sequence number that identifies the row, you have a meter ID, you have a timestamp, and then you have the JSON document describing the reading. And if that changes over time, let's say the device that's sending, let's say you upgrade the device to device 2.0, and now the readings are more sophisticated, more detailed, your data engine underneath doesn't have to change, right? Now, going back to JSON really quickly, the problem with JSON, which we'll address, is JSON's going to be slower, right, than a relational column. If I'm doing an aggregate or a predicate on this JSON document, it's going to be slower. I'm basically doing like some kind of string parsing. I have to go to this document and fetch out the attribute. So we'll talk about how we make that faster later. Okay, another thing that you need, okay, for this requirement is an easy capability of communicating between the device and your database. And this is where REST comes into place. It's the ideal protocol, we believe, for clients to connect with the underlying storage engine. So you want to connect through REST endpoints. So here you got your lightweight clients that are sending out a URI that has attributes associated with it that you then map and bind, and then generate SQL in this REST server process that generates SQL to the underlying database. And that does the put, if you will, or the get, if you will. And the database then responds back because it's got SQL results. It needs to send that back into JSON. So the SQL result comes out of the database into the server process that handles the REST endpoint and transforms that into JSON, and then JSON gets sent back to the lightweight client. Okay, simplifies and standardizes APIs to access data. We want that simplification so that any device can connect to your storage engine. Okay. The next thing is high-speed ingestion. So what we'll talk about now is an Oracle-specific technology that makes ingestion a lot faster. So we have a feature called mem-optimized row store, which brings fast ingestion into the database tier. And the idea here is we want to insert directly into memory. And once you insert directly into memory, you respond back saying, I'm done. So let's look at this picture here on the right. So you got these events coming from these sensors and different devices. And it's going to stream those events into an application server, right? That's kind of like in the mid-tier area. And on the right side, you see the database on the bottom as that disk picture, and you see the memory associated with that database. SGA stands for System Global Area, which is just the memory that's used, that's shared between different processes on the database. And you want those events to stream and be ingested directly into memory, into a pool of memory that we call the large pool. And once it gets buffered into that memory in batches, essentially. And after it gets buffered there, it immediately returns back to the application server and back to the device saying you're done. It's been ingested. The reality, though, is it hasn't been persisted. It's not in the database itself on disk. And so there's a risk associated with losing that data if your database goes down. So I'll talk about that in a second, but the main thing is you ingest the data very quickly into memory and you come back out telling the device, okay, send me your next batch. Now, what happens is we'll have drainer processes that are running in the background that will constantly look at these batches of events and flush them to disk, okay? So that's happening periodically as the buffers get full. Now, what happens if the database goes down, okay? If the database goes down, we have an API that allows the device, the developers to check to see if those inserts have been durabilized. So you, the developer of your device, can periodically check and say, hey, have you written up to this point? Yes or no? And if the API returns back saying no, that tells you, okay, something happened. I will go back and reinsert those events. Okay, so that's kind of end to end. This is what allows us to get to really rapid data ingestion. And we're just being optimistic about it that, hey, most likely your server will not go down. But if it goes down, you can check and see what's going on. Okay. I'm not going to go into too much detail about this because most databases have this, but it requires scale out. This is just basically scaling out your database. So here you see on the picture on the left, I don't just have one instance, I have two instances on something that we call RAC, or real application clusters. And RAC allows us to scale out your processing across multiple nodes or multiple servers. And with Oracle, all of these RAC instances share a common pool of storage. So as your data set grows, you want to be able to scale out and say, okay, let me add a new server to my cluster because I got a lot more devices bringing their events coming in. So I can scale out performance with RAC. I can scale out fault tolerance. So if an instance goes down, no problem, I can connect to another instance. And because the storage is shared, that instance can be able to still retrieve all the data sitting on that shared storage. Okay. That's the main point I want to make about that. Another thing now along the lines of fast ingestion is partitioning. You want to be able to partition your data as it's coming in because partitioning allows you to parallelize data ingestion. So let's look at this example on the left. At the very top, you got this temperature reading, right? There's some meter that you have or some sensor that's giving you temperature readings. And on the y-axis, you have interval partitions, which means I want to build a partition of your data from 6 p.m. to now, my hottest partition. My next hottest partition was my previous partition that went from 12 p.m. to 6 p.m. And before that was 6 a.m. to 12 p.m. And so I'm building these partitions of data every 6 hours. And once the 6 hours completes, I freeze that partition and I open up a new partition for data to come in. So that's on the y-axis. On the x-axis is going to be sub-partitioning. So I want to now partition with sub-partition within each partition based off of my sensor ID. So I don't want all of the sensors to go to one area within the partition. I want to distribute that workload across the partition. So by being able to partition and sub-partition, I'm able to move these events into different sub-partitions at the same time. And that allows me to parallelize data ingestion over time and by source ID. Okay, hopefully that makes sense. It avoids contention of space allocation. It's very important whenever you're dealing with scalability problems, again, in real world database, data storage engines, you want to be able to avoid contention on either space or time. And the way of doing that is kind of partitioning your workload. Okay. Now, this is taking it to the next level. So we talked about partitioning. We talked about scale out by adding multiple instances. This is now called sharding. And sharding is doing sort of geo scaling, if you will, meaning I want to partition based off my geography. So if my events are coming from all over the world, I want to keep the events that are in Asia. I want to keep the events that are coming from North America in North America. And basically, I want to have a single global view of a database, but in each one of these regions, they should be separate databases. So sharding is one giant database divided into several smaller databases. And this is super important, again, for scalability and availability issues. To avoid that, you want to be able to have separate shards. Okay. The rest of this is kind of more details here in terms of what I just said, but that's the idea. Okay, any questions so far again on that? If you do, feel free to add it on chat if you like, and I will continue to monitor on the chat side. Okay, so now we're moving on to real-time analytics. So how do we get immediate responses based off of the data being ingested? So we have a solution called database in memory, which is basically bringing a column store into your database, into our database. And now what's different about our database versus other databases out there when it comes to real-time analytics is we basically maintain two formats, I should say, of your data, two in-memory formats of your data. One is a row store or a row formatted version, which is great for doing transaction processing. And the other is column store, which is great for running analytics. So if you see in this picture over here, here's your row store, this is your column store. The data is a single copy of data sitting on disk. Your sales table is sitting right over here. And the optimizer then makes a decision. Should I go through the row store or should I go through the column store based off of the query that's running? Okay. This is not a separate engine that we plugged in. This is natively built into the data engine. And the benefit of this is that all of the existing things like the clustering we just talked about, the real application clusters or rack, that works seamlessly. Sharding, like we just talked about, works seamlessly. All these things just work. The trick is to make sure that these two stay active and consistent with each other. So any updates that happen to the data on disk get reflected in the in-memory formats that we have here. Okay. Very quickly, this is just a picture that shows how this works. We take the data that's sitting on disk in the row format, we populate it, we call this populate, to bring it into memory into columns, which means we have to transpose the rows into columns. We use interesting formats, data formats, dictionary encoding, run length encoding, things like that, to keep the data compressed and keep it in a format that can be queried without decompressing the data. Okay. Okay, so the key technologies that we have, number one, as I mentioned, column format. It allows you to access only the columns you care about. That saves you on I/O costs. And even within memory, I'm only running on just that column I care about. I avoid bringing into cache all those other columns. Vector processing, I don't know. I'm assuming you guys have talked about SIMD vector processing. Is that correct? Xiaoshang, I just want to make sure.
I probably mentioned it, but we don't discuss in detail.
Okay, no problem. So very quickly on this, this is huge for columnar databases. Columnar databases get their speed because when they operate on a column of data that is, could be compressed for dictionary encoding and so on, the way we do filtering is we grab a bunch of rows or column values at a time into a vector register, SIMD vector register. SIMD stands for single instruction, multiple data. And allows you to do evaluation on a batch of column values at a time. So this picture shows you, hey, let's say I had a column of states, California, Wisconsin, and so on. And I want to know which of these states is equal to California. So I load a batch of them into a single vector register. Let's say I load 64 of them at a time. And then in one cycle, I can do a 64 comparisons of each one of these to say which one's California. Okay, so that's how you get to billions of rows per second instead of millions of rows per second with a row store. Okay. We have something called storage indexes that allows you to do very fast pruning. So imagine you have a batch of rows here, a batch of rows, and a batch of rows. But we maintain the min and max values for each column within these batch of rows. So if I'm looking for a value of 9, well, I know it's not going to be in this batch because the min and the max 9 is outside of this range. It's outside of this range, and it's only inside of this range. So I can quickly say, this is the batch of columns I want to look at, not these. Okay. And the last thing that's very important is compression. We want to be able to keep this data in memory and be able to scan it very quickly. And for that reason, we really have to have solid compression technology to be able to achieve that. Okay, I'm just going to scan through this very quickly. All aspects of analytics for event stream processing, you need to be able to have very fast scans. You need to be able to join between dimension tables and fact tables very quickly. And you need to be able to do reporting, aggregation very quickly. So we have a lot of technology built around this to make scans, joins, and reporting faster. And I'm going to cover just a few of them in a bit. One thing I want to talk about now is how do we make mixed workloads faster? So when you think of an event stream processing solution, you are doing two things. You're ingesting your data. So a lot of new data is coming in and being inserted in. And you're also doing analytics against it. You're doing scans and joins and aggregation against it. So this is considered, in my mind, a mixed workload because I'm doing two things. I'm doing some DML operations. I'm changing my data. A lot of data can be coming out of order because not all devices are sending the events at the same time. So it takes a long time for it to come. So it can be out of order. So how do we make mixed workloads then faster? So in a mixed workload, you're typically going to have 1 to 3 indexes just to be able to quickly get to a row. These are called OLTP indexes. And then you're going to have a bunch of analytic indexes to do your fast scans or filtering and so on. And the problem with those analytic indexes when in a mixed workload is every time you do an update to your table or an insert into this table, all of these indexes have to be maintained. Every single one of them requires an update. And that's very, very expensive. And so what we claim is that you can replace those analytic indexes with just your column store. And now, whenever you do an update over here, you need to maintain it in the column store. But because that column store is not persistent, the updates are very fast. It just requires setting a bit. And we'll talk about that says, hey, this guy's been updated. And that's it. Okay, so we'll talk about that here, in fact. Okay, so let's go through this example. I'm going to skip through the words and just show you the animation. So you see that there's, again, our architecture, our row store here in memory, our column store here in memory, and the data sitting on disk. Now, let's say you do an update, okay, to this table. You want to update this row. It's going to update the row in your buffer cache in memory. It's going to say, okay, this row has XXXXX. It's been updated. Okay. Now, let's say you run a query. Okay, sorry, let me go back. So once that happens, what we do is every block of rows on disk are mapped to their location in memory. So as soon as you do an update to some row in some block, it's very quick to identify where in memory in your column store that was updated. And so we just have to have a bit vector that maintains mappings of rows to their location on disk and set a bit that says it's invalid. It's no longer valid to look at that in the column store. So now when you run a query, okay, that wants to do an analytic query, we go through all of the column values, but we skip the ones that are invalid and we keep going. Okay. So by skipping it, that means everything else is valid except that one. And so for just that one that's invalid, we will go back to the buffer cache to get its updated copy. So that's how we stay transactionally consistent between our column store and our row store. Okay, hopefully that makes sense. The only problem now is if there are too many invalid rows in the column store, it starts to become expensive. You're going to do this columnar scan that's going to skip a bunch of invalid rows, and then you're just going to go back to the row store to get those. You might as well potentially just go to the row store and do your analytics on it. So this is where we have techniques that will quickly refresh the copy in memory, the in-memory formatted version in the column store, so that it gets rid of the invalid rows and brings in the fresh rows so that everything is fresh and new. Okay, hopefully that makes sense. And that's, again, really important for event stores, because even though event store processing aren't doing really updates, they're doing inserts. And when you insert, you're also saying, hey, there's a hole in this column store because I brought something in that's new. Go here to go get it. And so that's why we want to make sure that this thing stays nice and fresh. Okay. Oh, there's some questions. Let me just look at this really quickly. What if only row store is down and column store is not? What if row store is inconsistent with column store? Which one is more trustworthy? Okay, so the row store is never, so as I mentioned, the row store has the truth. It's a source of truth. So the column store will simply say it's invalid, and that is always true. It's kept in lock with the row store in terms of that row being invalid. And so, as like I mentioned, as soon as we detect that that row is invalid in the column store, we go to the row store to fetch that row. And that's why whenever you run your query, it will always be correct. Okay. Can we join stream data? Don't we need to complete tables to perform joins? So yeah, so you can join a streaming tables with another table. And that's something that a database does very well at, whereas so for example, let's say you have streaming data that's coming in, and based off of that streaming data, you want to look at another table that maybe has spatial data that says, hey, based off of all these events are coming in, I want to know from my spatial data, which restaurant I should go to based off of all these high rankings that are coming in real time, or something like that. Okay. So then there is a join that happens where you're going to run your query against the streaming table, and then based off of the results of that, you'll join with another table that might be based off of location ID or something. And that's the primary key foreign key relationship between those two tables. And then you pull out relevant data from the other table. So yeah, you can do that. Okay, let me keep going. And what I'm gonna do is I'm just gonna spend a little bit of time just talking about a few key things on real-time analytics, and then I'll move on to the next requirement. So this is an example of how we make the column store real-time and as fast as possible. So let's just look at the picture here and ignore the words. Oftentimes you might run an expression like this. price plus price times tax. Okay, that's equal to your net price. Price plus price times tax. So you have to read the price column, you have to read the tax column, then you're going to do price times the tax column, and then you're going to add it to price again. Okay, now that can be expensive. What we want to do is say, why don't you tell us that this is a virtual column? Net is price plus price times tax. And once you tell us that this is a virtual column, we will go ahead and populate into the column store a new column, an added column, if you will, that is the materialization of that virtual column of price plus price times tax. So that the next time you run this, you're just going to go through here and you don't have to pay the cost of going through price and tax. Okay. You can do this manually. You can declare this manually, or we can auto detect that this is a very frequently executed expression, and we'll populate this ourselves. Okay. So I'll skip this example for date queries. It's a version of this. Let's skip that for now. And now I'm going to say how we make joins faster. So both joins and in-memory expressions, as you'll see from the demo slides, hopefully we'll have time to show you, will help us make event stream processing really fast. So here, how do we make joins fast? Well, let's suppose that you are joining a line item table with the orders table, okay? When you're joining these two tables on the order key, again, if you tell us by creating what we call a join group that you want to join these two tables, we do the following. We take your line item table, we look at the order keys. Okay, now these order keys could be random values. Now the line item table is the fact table, right? So it's going to have foreign keys of the order key. But you look at the orders table, and all of those orders are going to be distinct. They're going to be random values, but they're distinct. And you only have from 0 to, in this case, 2,698 distinct orders. Now, what we next do is we build this structure, what we call a global dictionary, and it maps orders to dense keys or dense values. And the maximum dense value is going to be 2,698 because that's the max number of distinct orders you have. Okay. And so all of these orders, order numbers get replaced with these dense global codes. Okay. So now what we do is we replace the hash join. Hash join involves taking this join key, hashing it, looking it up into a hash table, then doing a key comparison to make sure that these order keys are the same in order to be able to determine if you have a match. Instead, you can now convert that hash join to a very simple array lookup. So you got your code and you want to say, is there a match with the orders table or with the line item table? You look it up into this array in the orders table of just 2,698 entries. And if there's a hit, then there's a match. And if not, there's no match. And that's it. Everything is based off of now a simple random, potentially a random memory access. Okay, but that's it. It's an O1 lookup. And depending on the size of this, of how dense this is, it could be random or it may not. It may already be cached in your L1, L2, L3 CPU caches. Okay, hopefully that makes sense. That's how we make joins a lot faster there. Okay, now I'm going to skip through this converged workload, but the main thing I want to maintain here is in the column store, we maintain different representations for different data types. So for spatial, we have a unique representation of spatial so that spatial operations are faster. Same with text. We keep, instead of having your document, your text document here, or in addition to maintaining your text document here, we store a text index or an inverted index in the column store so that you can quickly match all documents, all resumes in this example that have the database keyword in it. So you can quickly get to it. Same thing with JSON. In the column store, we do something very unique, and I'll explain that in this next slide. we columnarize your JSON document. So if you look at this JSON, there are 3 JSON documents here, 1, 2, and 3, and they all have a first name. In this case, first name is John, Alan, Clara. So we take those documents and we create columns out of it, with name being the column name and all of the values, Alan, Clara, John. And then we do the same thing for all of the other paths that are in those JSON documents. And so we call these path value columns. And so now when you want to run a query that's a JSON query that's looking at age less than 34 and name equal to John and address city equal to Redwood City, these now become very fast SIMD vectorized scans on essentially relational columns. Okay, so this is how we make JSON faster. So now going back to event stream processing, where we're dealing with JSON documents as the attributes for every event, now you can see why we can run very fast predicates and filtering on those JSON docs, because we columnarize them and then we put them in memory, and so it goes a lot faster. Okay, 15x faster. All right, so I'm gonna largely skip this section, but just summarize it. Rich analytics query functionality, as I mentioned, it's very important. So analytic window functions allows you to do things like this, where you want to select the max energy over a partition of time. So for this is one window for 1 hour of readings. I want to know what was the max energy used. 2. For the next window, it was 1.5. So it's doing an aggregate within this window of time. And that's an example of very rich analytic functionality that you want your event stream processing system to be able to support. Okay, so I'll skip through the words over here. Similarly, if you can look on the right, you want to be able to do more complex analytics. So here I want to do what's called a match recognize that wants to look for specific patterns. So you can define a pattern here. So for example, let's say you're looking at the stock market. Ignore this for a second, but let's say you're looking at the stock market, and we all look at the stock market these days and it's down, down, down. But you're like trying to predict, when am I going to see this V-shape kind of graph on the stock market where all the stocks go back up again? And so you're looking for these V-shaped patterns. And that's a pattern that you can describe here and then run a match recognize function that will then look at all of your data, even the data that's coming in real time, and see, do I have a match that fits this pattern? So again, you need that behavior in your event stream processing system. And then the last thing here is you want to have machine learning capabilities, again, for the purposes of prediction. If you want to predict from whether there's going to be fraud that's happening based off of all of these new transactions that are coming in, or you want to do sentiment analysis based off of readings that are coming in from news feeds or spam filters. So you need to have that analytics capability in your system. Okay. Okay, more things there. Okay, and the last part I want to talk about from requirements is data lifecycle management. As I mentioned, when data comes in, it's coming into this write optimized region, if you will. Write optimized means I want to ingest the data efficiently. I want to optimize for write speeds. Then that data slowly moves into this read optimized category, which is saying, okay, I want to be able to do analytics. I want to be able to run real-time analytics on this data. That means I want to optimize it for read performance. And then the last thing is, okay, now the data's cooled down a little bit. Now I want to be space optimized. I want to be able to optimize this data for space and compress it or summarize it and so on. So that's what this bit says over here: write optimized zone, read optimized zone, space optimized zone. So how do we do this? We basically have a way of automating movement, data movement from one region into another. And I think I have a point over here. Yeah, right here at the bottom. Okay, so this gradient of write, read, and space optimization is achieved with something that we call automatic data optimization and a DBMS scheduler. What these two things do is they say, allows you to create a policy, if you will, that says after 1 hour of no writes or no updates to this event, compress it. For example, I'm just giving you an example. Or after this partition has exceeded 1 hour, compress it or move it to a different tier. So this kind of facility to automatically compress your data or reformat your data over time is important. And we have a scheduler capability to make that happen. Okay. Last thing is called downsampling, and this is just a very simple concept that says, hey, your meter readings have been these very large 6-hour readings. Every 6-hour readings, you do 5-minute consumptions every, within a 6-hour partition. Now, I want to summarize all this into essentially 60-minute consumptions. So for every 12 readings here, that 12 times 5 makes 60, I want to be able to have a single event that captures those 12 events. And that's called downsampling. It's basically saying, hey, I want to round off or summarize that data. So downsampling, again, can be achieved through the combination of that scheduling capability and the automatic data optimizations feature. All right, so this is the last summary slide, and I'm just going to show you some demo slides really quickly. And this just says, look, for event stream processing, we need that flexible data model. We use JSON for that. We want high-speed ingestion. We talked about all these things over here with partitioning and mem-optimized tables and rack for clustering and sharding and all that stuff for ingestion. We want streaming analytics capability, right? We want a very rich analytics library. We want real-time analytics, and that's where database and memory comes into the picture. And then the last thing is the automatic event lifecycle management, where you want to be able to do automatic compression using a scheduler capability. Okay. Okay, so what I wanted to show you guys now is just a quick set of demo slides that shows you how we deal with DevOps monitoring. So DevOps monitoring, if you look at the picture on the right, is very simple. The idea is, like, we're Oracle Cloud. We have Oracle Cloud. There's Amazon, Google Cloud. Everybody basically has a fleet of servers where you as an application, or customers running your application on them. And we need to make sure that those servers are running up to speed, right? We want to make sure that there's no downtime that the customer is going to experience. So these servers are giving off metrics, things like CPU utilization, things like memory availability, disk space availability, all that stuff. And those metrics are going to be streaming into an event stream processing database. And from there, you're going to run queries against it, things to do like anomaly detection, which server out of all my servers has exceeded its server temperature. You want to generate reports again, or dashboards. Okay, bottom line is you want to do some anomalous detection. Okay, so that's DevOps monitoring. Now, we looked at Prometheus, and I don't know how many of you have heard of Prometheus, but it's a very popular monitoring, open source monitoring and alerting solution. And they build a whole ecosystem out of it. So they begin with their own storage engine, their own database, if you will, that's like a Timeseries database. And on the left side, they have what's called data exporters, which is for every server, every system that you want to monitor, you run an application called a data exporter that collects metrics. And the data storage engine pulls those metrics into the data engine. Okay, so that's how it gathers it. Now, on the right side, to run your queries, you run with Grafana that allows you to generate dashboards, and you can run queries against it using PromQL, their own language. And then it allows you, the data engine itself allows you to generate alerts. So it says like, hey, if a specific threshold has been exceeded, go ahead and fire off an email saying, hey, the alert has been reached, threshold has been reached. So this is their whole ecosystem. And to kind of prototype this, so the initial prototype, we took away Prometheus. Okay, we wanted to say, hey, what happens if we take away Prometheus and just replace it with Oracle? So we did that. We got rid of the Prometheus engine and we replaced it with Oracle. And then we added all of those cool technologies we talked about. We brought in rack for scale out. We brought in partitioning support. We used our own user-defined functions to be able to pull metrics from those exporters. We had the mem optimized for write to be able to ingest directly into memory. Then we used JSON to store the data, database memory for real-time analytics, a new plugin for Grafana to be able to run queries, et cetera, et cetera. Okay, we brought in the compression aspects of it, all of that stuff we used so that the whole ecosystem stayed in place, but we just replaced the Prometheus data engine with Oracle. Okay, and that was our prototype, and we were able to show that everything worked fine. We were able to ingest data directly into the database. We were able to run the queries just fine through Grafana, and that proved that, okay, we can do this. And then now for the real demo, what we did recently is there's a real product out there called Exadata Real-Time Insights. And what this is on our Exadata database machines. These are machines that are in the cloud that our customers are running on, their applications on. And we, with Exadata Real-Time Insights, it's generating those metrics. Okay, so it's a DevOps monitoring solution. It generates these statistics and those metrics for us to observe and monitor. Okay, in our setup, in the real setup, we have over 2,000 events that are collected from each and every single server every second. Okay, and all those metrics that we talked about are what collected. Okay, so then what we did is we're going to build this demo that monitors over 500 Exadata servers in the real Oracle data center in real time. And this came out to about 2.5 billion Exadata metrics captured over a 24-hour period in one day. And then we showed in this demo how we're able to detect anomalous behavior very quickly using database and memory for real-time analytics versus without database and memory. Okay, so the setup was like this. You had all these Exadata machines. This is an example reading. An example metric value was a temperature. Its value is 25 degrees Celsius. Here's the timestamp. And then these are the attributes. It came from this fleet in Phoenix. The server name was this. There's a unit value in Celsius. So that's an example metric. We use, again, the database server. We use the REST facilities to ingest the data. Again, we had interval partitioning and used JSON storage. We had Grafana to show the dashboard, and we were able to use that to run queries against it. Okay, and of course, database and memory. Let's skip through that. So what we did right off the bat is there's a database overview page. It shows over 24-hour summary. This is how many metrics you're able to get. The data size is almost 450 gigabytes. In memory, we compressed it by 16.4x. So again, this compression is very important because we want to keep this data as much as possible in memory. So compression is super important. Okay. Then we looked at a 1-hour summary without in memory. When you're running this dashboard, these dashboard queries are running in real time. And it's saying in this 1 hour, I wanted to know how many metrics were there, how many of those metrics came from how many different fleets, and how many different storage engines, database servers and storage servers were there. So you can see that in that 1 hour, you can't tell because I'm not running the demo live, but it pops up very quickly. And without in memory, it's still spinning. Because this is our first indication that it takes some time to run these queries without in memory. Now, why? Why does it take time? So look at this query that's actually being ran, okay? The query has 3 different important things. One, it's doing a JSON lookup. JSON value. It's trying to say, give me the server names, okay? Now, as I mentioned, why is in memory faster? Because we do columnar JSON. We take each of those columns, those attributes in JSON, we make them columns. So that's going to be number one, why we're faster. Number two, it's a like predicate. Okay, so any of these filters that we do, we make those scans really, really fast. So there's a like predicate. And then the last thing is aggregation, count, distinct. Again, within memory in our data formats, we can do aggregation, count, distinct, all that stuff, an order of magnitude faster than without in memory. Okay, so this last slide, let me check my time. I have one more minute, let's say. This last thing just shows, hey, I want to now detect a specific problem with a server. So this is an example where I check to see, find me any servers that are hotter than 40 degrees. And it popped up one of them. One server is hot. Now, with no in memory, it's still spinning. Okay, that's the idea. The idea is we want to be able to dive deep into the problem, look into this server right away, so that we can figure out what's going on. So I dive into the server and I say, yep, this storage server was hot right here. It went to 40 degrees Celsius right around this time. And then it dropped for whatever reasons, okay? It was going up, got hot, then it dropped. So, okay, fine. Now I look at the disk controller battery and it says, okay, that also was hot around that same time. That's really odd. And I look at the storage server CPU and says, well, before it got hot, there was some CPU activity, 50% all the way up to about 70%. So something was running, not really hot, but it was hot. And then I look at the last metric, it says working fans. And you can see from the working fans, we went from 12 working fans all the way down to 2, right around the time when the temperature exceeded. And you can say, okay, there's not a root cause, but definitely an explanation. Something might be wrong with the working fans. Something may have caused the working fans, but it went back up. So that tells the IT person there to go look at that server, check on the working fans. Okay. So while that whole investigation happens, we show that, hey, without in memory, you're still spinning. Okay, that's the real-time analytics part is I can quickly determine what the problem is. Okay. All right. So that's it. I want to just go past this really quickly, skip through these slides, and just simply talk about the research and development opportunities in this space. We care about compression. We care about hardware acceleration. How do I make these different workloads like event stream processing run even faster on different hardware with GPUs and FPGAs and so on? There's something called approximate indexes. You should learn about that if you haven't read about that, but that's another area of good research in this space. Machine learning, mixed workloads, in-memory technology, all of these are kind of active engagements that we are involved in as an organization to make this specific workload run faster, let alone all of the other workloads that we're trying to optimize, right? The different technologies that they're investigating. Okay, so thank you. I apologize for going right at that time, but I hope that was helpful.